How can we best power our research in space or in the deep ocean? Marianna Rogers is a graduate student at MIT's Department of Mechanical Engineering who studies how structures, like carbon nanotubes, can store energy. Let's join Marianna for her MIT abstract to learn about the research that goes into building and testing these special materials.
Hi everyone! I'm very excited to be here and to talk to you all about powering the future. So this is going to be my presentation. How can we power the future and how can structures store energy, right? So when I mean that something is structural, I mean that it is strong enough to hold weight or keep its shape. So let's keep that in mind throughout the presentation here. So first off, I'm Marianna. I'm a graduate student in mechanical engineering at MIT. So what I do there is work on creating materials that both store energy and are super strong, right? So we take materials like this over here on the right and try to make something big and useful with them. So the goal in specific is to help make these things like bikes, cars, planes, and maybe even your backpacks lighter, stronger, and able to store energy at the same time. So I want you guys to all think for a moment. Imagine if your backpack could hold both your books and charge your phone at the same time. Wouldn't that be really cool? Well, can you think of a single material that does this? Both stores electrical energy while being super strong? Now, I'm not just talking about devices like a remote, like we have here, right? That have a hard, strong shell and then a separate compartment for batteries that allows it to store energy, as you can see here, right? I am talking about having a single remote like this, that if we were to use to make a single material, that would both be strong and hold electrical energy, right? And that would be a simultaneous thing, so not a separate thing like you saw in the remote before. So it turns out making one material do both jobs is really hard. It's kind of like trying to make a brick that also works as a sponge. Imagine building a house out of sponges or trying to, clean up a spill with a brick. It doesn't really work too well, does it? So think of a battery as a delicate science experiment inside a small box. Batteries are just one way to store energy, just like sponges are just one way to soak and hold liquid. Think of towels, paper, etc. And they do so in a chemical way, these batteries, right? And the important thing to note is that they're very fragile and soft inside, and there's lots of sensitive chemistry happening. And so that's why they don't really like being bent or crushed. So how is it used in everyday life, these batteries? So this is how batteries look like in everyday life, particularly in common electronic devices. Over here, there's an electric car where the batteries are located down here on the bottom of the car. And then we have a laptop as well as a smartphone. You can see how much space, weight, and weight these batteries take up. They're over here, as you can see very closely. This is where the batteries are, and this large block here is also a battery for our smartphone. So because of the amount of space and weight that they take up, incorporating energy storage into the actual material of these devices would make these devices super efficient. So I study carbon nanotubes. So why do I study carbon nanotubes? First off, carbon nanotubes are one of the strongest materials ever discovered. They are stronger than steel. They're special because they are both super strong, but also great at handling electricity. So it's a single material that is both really strong and can handle electricity at the same time, right? Not something you can really think of, very common. So the only problem is that carbon nanotubes are super tiny. They're 10,000 to 100,000 times thinner than a human hair. So their features are on a very tiny scale, a scale that we actually call a nanoscale. So it's really hard to join millions of them together to make something big and useful. So here we have a diagram that will hopefully give you a good scale for how small these nanotubes are. So on the right here we have the size of a human hair, followed by a grain of sand, and then a grain of salt. And then down we go to, a grain of pollen, to even, a red blood cell. And then all the way down here, if you follow my cursor, we would have our carbon nanotube, which we wouldn't even be able to see clearly. Just look at how small it is compared to the width of your hair. So that's why it's really hard to work with these kinds of materials. They're just so small. Luckily, we've been able to make lots of CNTs in our lab, next lab at MIT, that you can actually see. So This is what happens when you grow millions or billions or even trillions of nanotubes together. They form a piece of material that's big enough to touch and work with. So think of one CNT like a single pixel on the screen. You can't really see the whole picture with just one. But when you put millions of pixels together, you finally start to see something like we have here, right? So this is our pixel, and then this is our big picture. So now that because we have something large enough to touch and work with, we are on the right path to making this idea of applying carbon nanotubes as a material to build different things like laptops, planes, and even satellites a reality. Of course, there's still a lot of work to be done. Energy storage devices need multiple different components to work well together, so we are currently working towards that. But that's the dream, applying it to these different things. So why did I specifically become interested in this topic? Well, not only is this a super challenging area of research, something that has never been done before, I really went into this kind of research to better explore and withstand extreme environments. So I love exploring the world and wanted to make our world easier, safer, and more efficient to explore by solving the many problems and challenges that come with exploration, especially in extreme environments and extreme conditions. So over here, you actually can see me walking on a trail that is basically a river in a canyon. And over here, after hiking the highest point in Texas, we actually were treated with a really nice rainbow at the end of the trail. So yeah, we have different landscapes here. This is also a canyon in Arizona. This is in Utah, also Utah, a lot of Utah, I like Utah a lot. And in Montana, at the highest points in Glacier National Park. So obviously I really like to hike and go to the tops of mountains, but I also really like to scuba dive. So you can see me here, and I'm right here waving a little bit, and I'm scuba diving. So here I'm scuba diving again, but now you're seeing me move through water since I'm underwater. Underwater environments, especially at great depths, are considered extreme environments. One reason for that is that you start to feel an increase in pressure. Have you ever gone deep enough in a pool or a lake where your ears started to hurt? If you have, well, that's because you're experiencing pressure from the weight of the water. There's also no air underwater for us to breathe. So that's a problem for us humans, right? That's why we need to bring an air source, which is the scuba tank right here that you see attached to the backs of these people. Now, these tanks are made of aluminum and sometimes steel, so they are strong enough to withstand the high pressures experienced at depth. But other materials aren't so lucky. So we know that the deeper we go underwater, the more pressure is exerted. But even if we take steel and aluminum down to 2,000 meters below the surface of the ocean, where the pressure is about 200 times the atmospheric pressure, they won't compress too much, only a very slight amount. But on the other hand, if we take styrofoam, which you can see here, we've all taken drinks out of a styrofoam cup. If we take that 2,000 meters below the surface of the ocean, then you actually see that it shrinks. And that's because of the pressure that it has to undergo 200 times that pressure that we feel here on Earth, on the top of, at sea level. You start to see that it shrinks, and it shrinks a considerable amount. So that gives you a good picture of how much pressure is down there. It also means that's why materials matter so much when we talk about exploring different environments, especially when we're choosing and making the right ones that meet our needs for these different environments. And it's because of these materials, like the metal tanks, that work well with their environments, that we are able to explore extreme environments, like when we scuba dive. So this, of course, applies to robots that do some of the exploring for us. If you look at the drone over here, for instance, you want materials that are able to withstand the conditions of wherever that drone is going to go, whether that's a super cold place or a super hot one. Same thing goes for these underwater robots, like this one, or vehicles if you'd like to call them. Like the scuba tanks, they need to withstand strong pressures at depth, among many other things. But now we have to consider, how do we power these robots, right? Well, these robots are all dependent on batteries. This past summer, I was in the middle of the Atlantic Ocean, actually, with some oceanographers, marine scientists, and marine robotics engineers, tackling and learning about big marine robotics problems. And you can see me here holding a marine robot. And one of the biggest complaints they all had was how much their data collection was limited by battery life. So we want to make sure that we make these materials that are efficient, both strong and can store energy in order to increase missions, increase the data collection for these oceanographers, etc. But another parameter that we also want to look at when considering our materials is the weight. Their weight matters, and in space that matters a lot. So it matters because if you decrease the weight, you're able to basically use less fuel, and that makes the whole mission less expensive. And that makes it easier to explore space. So this same reasoning also applies to airplanes. With less weight, basically, we are able to take more stuff onto the plane or go longer distances. So remember carbon nanotubes? Well, yeah, they're great materials to use on space and aircraft, and that's because they're lightweight and strong and electrically conductive, but really because they're very lightweight. So when we work with materials that could be good for space, sometimes we need to test them in space-like environments where there's no gravity. It would be very difficult to send things to space to test them frequently, right? So, is it possible to do that on Earth? Well, yeah, and one way to do that is using a plane. When you go on a roller coaster and when you reach the very top, the peak, you feel yourself lift off your seat a little bit? Well, that is exactly what this plane does. It goes up and down in like this parabolic path that you see here, like a roller coaster, and creates a longer sustained free fall. In this way, we feel weightless for a couple seconds, 20 to 30 seconds to be exact, and are able to study things on these flights because of that weightlessness that we experience. So yeah, think of it as a big roller coaster with lots of ups and downs, and that feeling that you feel at the very top of a roller coaster is extended to 20 to 30 seconds, and we do that about 20 times. So it's a lot of fun. So here I am in one of those planes testing my materials to see if gravity affects how it stores energy. You can see my experimental setup in the left image over here, my laptop, my equipment, and then the material testing here. And then you see me floating here on the right hand image. And you can see here how weightlessness looks like. Yeah, it was kind of hard to stay in one place while I monitored the experiment, as you can clearly see. And we actually all had these like ropes on the sides here of the plane that we would hold on to keep us in our general area. But it was definitely a lot of fun. So the end goal is to take what we have in the lab, something, let's say like this, and turn it into something like this, where we can actually make these materials work in a way where they can be practically implemented and create things like laptops, planes, even satellites. The reality is, there's still a ton of work to do. So basically with that, I conclude my talk and am happy to answer any questions that you may have. Thank you all for tuning in and for listening.
Thank you so much, Marianna, for sharing your research with us today. So we have a question from Pari on that. And you mentioned you're working with trillions of these nanotubes to build these structures. Pari's wondering, how long does it take to build one of these structures? And can you share a little bit about how much it costs?
Yeah, absolutely. So Perry, very, very good question. Very excellent. And that is exactly how a good engineer thinks about these things. It doesn't take as long as you think, because I know they're small, but we use a process where essentially we take a carbon source in a gaseous form and we react it with a lot of different things in an oven actually. So we heat things up and create chemistries, and we're able to grow these carbon nanotubes, and it only takes, really in reality 30 minutes, but the whole process will take an hour to an hour and a half. But it's a process, and we flow a bunch of chemicals and, gases, and then we basically grow them on a little plate. It's a substrate there. It's actually called a silicon wafer, but that's not too important. We basically grow them on a little thing, and they like to grow on that, and so we grow them from there. And that takes around, like I said, like an hour, I would say. And it is expensive just because it's in a research lab. So we use gases like helium and a lot of other things. So, you have to take that into account for sure. So it's at a research level. So it does get a little expensive, but they're actually now making it more manufacturable. So when you just start to make things manufacturable and make them practical in the real world, they can't be that costly. Some things are, but they can't be that costly. And so there's been ways to kind of decrease the costs in this way. And there's a company now in France that's doing that. So it's really, really cool.
Cool. So maybe that means one day the people tuning into this call, the Nord Anglia students and us, we can all work with these maybe one day because these seem like really, really special materials. We
Yes.
have a follow-up question from Arish now, and Arish is wondering, you mentioned testing these structures that you're building with carbon nanotubes in your zero-G flight and in space-like conditions. But Arish is wondering, how does this relate to water? You mentioned your interest in scuba diving. Have you also focused on taking these materials down to face that high pressure?
Yeah, so great question, Arish. Yeah, I would love to, but there's a lot of other things to think about, right? So we still haven't made a material yet that has been able to do two things at once very, very well. And then taking it down into water, well, you have to think about ways to kind of like isolate it from water or right like having a coating in some sort of way because energy and water don't work too well. But yeah, that was kind of the idea of why I went this summer to this, speak to all these oceanographers and marine scientists, and especially the marine robotics engineers, to try to kind of bring different perspectives of different things that we're working with. I would love to see them in some sort of capacity. I see it's again a very big challenge, and it would be great to use them in some sort of way, at least in a structural way. It might be a little bit more possible, and then obviously everything's possible, but trying to use something that has the energy is a very big challenge. But it's something that I would love to somehow do, but it's very difficult, and I have not yet done that. It would be really fun.
Maybe one day in the future, that could be something that you'll be able to test once you've planned it out and coordinated with all these other scientists and engineers. And now we
Yes.
have a question from Ashray. And Ashray's wondering, you're mentioning this really exciting carbon nanotube work. And Ashray's wondering, do you also do research on graphene?
Oh, great, Ashray. Yeah, so you're familiar with the nanomaterials. That's great. So my lab specifically doesn't do work with graphene, but yes, so basically for those who are watching, graphene, so carbon nanotubes, you saw that they were a tube, right? And they're composed of carbon atoms, right, in a hexagonal pattern, and then, they're rolled up into a tube. Graphene is basically the tube rolled out into a sheet. It's just like a paper, right, of carbon atoms. And so, yeah, graphene, we don't do any work, but there's a lot of work being done in other labs at MIT, especially, but everywhere with graphene. And they are working with them as structural materials, also as semiconductors because of their electrical properties. There's a lot of applications with graphene as well, but we don't work with graphene.
Got it. And now we have a question from Yazini. And Yazini's wondering, how long do carbon nanotubes, or how long are carbon nanotubes capable of holding any charge? How well do they hold energy and for how long?
Great question. Well, if you take it right, like, and it's basically a really good electrical conductor, right? So you have they kind of act as highways for these electrons to go through, and so when you have your carbon nanotubes and you apply some sort of electrical current to it, they just conduct these. There's very low resistance, so they're a great pathway for that. Now, when you want to talk about storing charge, right, and storing this energy, it depends on the kind of device that you're going to make, so the kind of way that you're going to store energy. And there's different, I mentioned batteries, and I said how that was only one way that you could store energy. There's also capacitors, supercapacitors, and there's various different ways to store energy, but they can store it for a good amount of time, in capacitors specifically. And we're working on actually making that a real all of these devices, they'll deplete after some time, especially capacitors, if there's a leaking or something. And so those are one of those challenges that we work on, trying to make sure that they sustain for some time. And it could be on the order of, obviously we want them to be on the order of days, definitely hours, but definitely, yeah, it holds charge.
Really cool. So then they are really, really good at transmitting this energy, and you guys are currently working on other systems in place that can kind of be attached that can store some of that energy. That is really, really cool. Nanratha is wondering, why are carbon nanotubes stronger than steel? You mentioned that in your talk. What's going
Yeah.
on there?
Yeah, it's crazy. Basically, it's because they're at such a small scale that the bonds that are at a place, right? These carbon atoms, the way that they're bonded to one another, they're really, really strong at that nanoscale. And so when you pull on them, so we test strength by basically pulling on materials. So when we pull on steel, it's very, very strong, and it can go up to 200 gigapascals for those who are interested in values. And they're very, very strong. But carbon nanotubes are at that scale. It's a very funny thing. If you've seen I don't want to mention this too much, but like Ant-Man, because it's still fiction, right? Ant-Man, where you go down to the scale and they have incredible super strength and whatnot. Basically, yeah, the materials and the world and reality works very, very different on the nanoscale than it does here on the macro scale. And that's because of the way things are bonded and how relative the size of those things are compared to the atoms and the bonding of those things. So yeah, so you have this very, very small thing with all of this bonding, basically relative to its size. And so these bonds are just really, really strong at that scale. And so they're very strong. So that's a big challenge, because it's a very good question, because when you start to make them bigger or make more of them, they lose that because they're becoming bigger. They're on the macro scale now instead of the nanoscale. And so they don't have that same advantage, I guess, if you'd say, as being on the nanoscale. And so that's something that my lab for many years has been working to improve, to try to retain those strong properties of the carbon nanotube and trying to keep them present even when you make them big and you bring them up to a scale where we can see. Great question.
That is so cool to think about, and it's surprising to know that you make it bigger to the point that you can see it, and then it's weaker because of its size. So I'm wondering, as you're dealing with these things on the nano scale, how do you actually see what you're working with?
Yeah. So great question. Yeah. So there are many. Yeah. So you can't really see it right with your eyes, but luckily, many scientists and inventors before me have come up with different ways to be able to see things at such a small scale, right? There's different kinds of, your optical microscope, you can see that, and you can see things, very, very small things with that. You can't quite see carbon nanotubes, at least very nicely how I showed it, right? Like that was actually an animation, but you can see carbon nanotubes through imaging techniques. And some of those are called, transmission electron microscopy, right? TEMs. So that is the way that you see carbon nanotubes, single individual carbon nanotubes at that size, right? We also use the scanning electron microscopy to be able to see just how I showed you that big material of many carbon nanotubes. Well, we use SEM to kind of see all of those at a smaller scale, but you can't really see individual ones. You just kind of see fibers, right? So that's why we use them. We want to make them act like fibers. But with the TEM, for instance, you are able to use electrons, also the SEM, but the TEM is a smaller scale, electrons to actually see how big and the actual carbon nanotube through that. And it's a very interesting thing. You guys should look it up. I can give a whole talk on that too, but it's a very interesting science, basically using the wavelength of an electron to be able to see and image these things. Very, very cool.
Wow, that is really neat. So, you're using different kinds of microscope techniques here, all the way from optical to transmission electron microscopes to scanning electron microscopes. That is really, really cool. And now we have a question from Abhay, and Abhay's wondering, thinking of that animation you showed us of these really special bonds that are between the carbon atoms here. Abhay's wondering, are these bonds covalent or ionic?
These are actually, yeah, they're covalent bonds that you can see here. They're very, very strong, and they're very exciting. But yeah.
Thank you. That is really cool to think about, and the bonds there. Namrata is now wondering, what are some of the challenges that exist in producing these carbon nanotubes in larger quantities? What's stopping us from producing these in huge amounts?
Great question. Yeah. So carbon nanotubes, basically the limiting factor is the size that we can get them, right? Which is something you pinpointed. Um, and what's limiting it is basically the size. So we use furnaces to build these materials, and that makes it cheaper, faster. And so essentially the sizes of these furnaces, how big you can make them, is the limiting factor. Now, in our lab in specific, we grow them on silicon wafers, right? So silicon wafers are the substrate, the plate that I was kind of talking to you about, where they grow from. They are limited also because they're a certain element that's used to create a certain wafer, right? And it can only be so big. And in recent years, they've been able to increase the size of those wafers, the diameter, because they're circular, right? They've been able to increase the size of those wafers. So that's a limiting factor for sure. You can't just have infinite length of these silicon wafers, these plates for these carbon nanotubes to grow up. But really, the biggest limiting factor in our lab and in general is just how big you can make these furnaces. And once you become big enough, and let's say you make a big furnace, then it would come down to the size of the substrate that you're using, so the silicon wafer.
Wow, so there's a lot to consider when you're trying to achieve the production of a certain quantity here. And now we have a clarifying question from Ashray. You've spoken about the bonds, you've spoken about the scale of these carbon nanotubes, and Ashray's wondering, what are the carbon nanotubes made of? Are there ever other elements, put in them to make them have different properties, for example?
Interesting. Very, very interesting. Yes, I guess. Yeah. So in our lab also actually, we basically also grow boron nitride nanotubes. So it's not really kind of embedding it, I guess. It's kind of actually taking these carbon nanotubes, coating them with boron nitride, and then burning off all the carbon and basically using that carbon nanotube as a scaffold, and you're left with these boron nitride nanotubes. So yeah, there's ways to kind of put things on you can functionalize them and whatnot, but you can put things on these carbon nanotubes and definitely manipulate them. And there's so much stuff being worked on and done, but in our lab in specific, this is a good example of a way that you kind of use them and you kind of put things on the carbon nanotube. Yeah, we kind of just coat them with that and then are left with boron nitride nanotubes. The same, yeah, structure.
That is really cool. So it seems like the possibilities are sort of endless there in what you can do using these carbon nanotubes as a base material in your experiments. I want to change the discussion now to kind of discuss your zero G work and testing these
Awesome.
structures in the zero gravity conditions. And so Keith is wondering, how many no gravity stations are there in the world, and can they be available for the general public to test, something that they build?
Interesting question. Yeah, so from what I'm aware of, if you're talking about studying, and working, like trying to use a microgravity environment here on Earth, I think there's that zero G company. So I think that's the only like companies for profit kind of entity that actually does these flights. I think NASA definitely has their own flight that does that. I think there's now a Canadian flight that does it, and then a European one, maybe a French one. But yeah, I'm not too sure on the exact, but there's only a few amount of planes that actually go and do this. So that's a really good question, Keith. Yeah, there's only a few. Mostly, at least here in the US, the zero G, unless you're an astronaut and you can go on these NASA sponsored ones. But yeah, and then space stations is basically the International Space Station up there in orbit, right? The ISS. And there are some experiments that are done there too. Someone in my lab actually just sent a piece of their material up there to test. So you can test things up there. But yeah, to kind of do that here on Earth, it would be through those avenues. So it's kind of hard. It's very limited.
Yeah. So it takes a lot of planning and applying to programs like Zero G, or becoming an astronaut, or submitting something to be on, for example, the International Space Station, or working with the European Space Agency. Got it. Okay. So there's a lot of work that needs to happen before we can test our own experiments in zero gravity. And now Alexa from Boston is wondering, what's the most interesting thing you saw or noticed when you were on the Zero G flight? Anything that sticks out in your memory?
Very good question. That's cool. I like thinking about it. I guess the most interesting thing was seeing my hair. So I don't know if it's what I saw, but definitely what I felt was the weightlessness, which is very different, very unique. It's like being in water, but without the water, without that resistance. But my hair, it's a little shorter now, but I had very like longer hair, and you can see in the videos it kind of goes up. My head felt so light. It felt so light because there was no gravity pulling it down. So it was a very weird feeling because I've always had a head full of hair. And so it definitely was the weirdest and most interesting thing because I was like, wait, what? It's actually a lot lighter than what you feel. And another cool thing was in one of those videos, also to my left, was Professor Jeffrey Hoffman. He's a former astronaut and a MIT professor right now. And he was he misses that environment, right, since he was an astronaut. So it was really, really fun and cool to see how excited he was. And he immediately we were all experiencing it, not all of us, but most of us experiencing it for the first time. And I just saw him shoot up. He knew exactly, he felt at home just moving around, and he was very intuitive with how he moved around the space because you're moving in 3D. It's very different now, right? And so that was really fun to see. He was a pro at that for sure, and it was really fun to see him back in his element.
That is just so cool. And I hope, Mariana, you'll have an opportunity to go on a zero G flight again and use some of you gained intuition for what to do when you're at zero gravity. And now I just wanted to follow up. We have a question from Namrata, and Namrata's wondering, what is the difference between zero gravity and microgravity?
Good question. Okay, good question, Namrata. So yeah, zero gravity is basically what it means. There's no gravity at all. Just zero gravity, and there's no gravity. Now in microgravity, we call it microgravity. You feel zero gravity, but you're not. There's still gravity, right? So that's the roller coaster effect, right? Like you're not escaping Earth's pull. You're just kind of in this state of free fall where you feel like you're kind of weightless, but there's still gravity. So that's why we call it microgravity. And that's a really, really good question because definitely people use it interchangeably, and it's not really interchangeably. So good catch.
Great question. And so I wonder, Mariana, if you can walk us through what a typical day looks like for you at MIT. What is a day in the life,
Yeah,
Mariana?
day in the life. Yeah, so definitely wake up like every normal person, right? Yeah. So I'm just like all of you. I wake up, and just like all of you, I also go to school, right? So I do my research, and I'm a scientist in that way. But I also am a grad student, which means I still go to school and I still take classes. So sometimes, depending on the semester, I'm a little more flexible. Some semesters I don't need to take classes, some semesters I do. But in the ones that I do, I wake up, I go to class. But I spend a lot of time, right, either in the office, which is where we're, answering emails, working on papers, on conference submissions, all that kind of stuff, which is what grad students do. But then also working in the lab, right? So working in the lab, and that that takes a while. And when you're working on things like batteries or energy storage that have a lot of the times ionic liquid, right? There's certain chemistries that can't be exposed to the air that we have here. So a place where I spend a lot of my time is a place called the glove box. It's basically a box where it has its own atmosphere. It doesn't have any oxygen in it. And I wish I had a picture. Maybe I should have put a picture. But these gloves that kind of like you can put your hands through to kind of work inside that box, but you're not, entering it in sort of way because it's sealed. And you're going and you're basically making these materials and creating these things in this glove box with huge gloves, by the way, because I have very small hands and it's a one size fit all, so they're huge. So trying to work with very delicate things with gloves that fit you like 2 or 3 times too big. And yeah, so I spend a lot of time there. That's exactly, in the lab, right? And in this glove box that we talk here, creating these materials and making sure that they're contained in a way that best improves their performance.
Got it. That is really, really cool. Okay, I
Yeah.
want to ask a couple more questions before we have to go. Ashray's mentioned that, you showed scuba and that you have these really interesting hobbies of your scuba diving and hiking. And Ashray's wondering, what are some animals that you've found when you've been scuba diving or hiking? And Ashray
Oh,
mentions that Ashray really likes biology and is really interested in marine biology and herpetology. So what have you encountered, Mariana?
that's awesome, Osprey. It's a great. I also love, biology, and that's one of the reasons why I like exploring, the natural sciences, all of that. So that's awesome. Yes. One of my favorite things that I ever saw, definitely down, and it was actually a very funny story. And in scuba diving, it was an octopus. Definitely an octopus. I've also seen a shark. My first time scuba diving, actually, and we went to depths that were lower to try to see it. Not very safe, but like the guide said this was kind of safe enough, and so it went, just at the limit. We didn't go below, but just at the limit. But it was really fast, and so I could really feel that pressure in my ears. But the shark was really cool. The jellyfish. So I'm not jellyfish. The octopus. I definitely have seen jellyfish too, but the octopus in specific. So there were two in one dive. That I did. And the first time I didn't see it, and I didn't know. We resurfaced, and people said that they saw the octopus. I'm like, no, I didn't see it. So we went back down, and we saw a different one. So that was really like just the feeling of, okay, I got a chance to see it, and that was awesome. So that was a lot of fun. So I've seen that. I've seen stingrays, a lot of different fish. They're really, really cool, but the stingrays are really awesome. And then hiking, I've seen grizzly bears, I've seen black bears. So those are like one of the bigger ones. Yeah, up especially in Wyoming area, that kind of area. So that's a lot of fun. Definitely. And actually I saw grizzly bears with their cubs. So that was really cool. What else? I've seen a lot. Yeah, a lot of different kinds of things, and even insects. Right? They're all over the place, and there's a lot of different kinds of animals that you see. Oh, elk. Yeah, all sorts. I can go through a whole. Oh, and then once you go up there, also the buffalo. You start to see them too, and they're really funny. Stay safe and stay away, but they're very, very cool to see from afar.
Yes, all of these animals are good at a safe distance, and it's so neat that you got to see so many. For our last question, I think we have a lot of students on the call who may be interested in, following your path and working on building these sorts of very special structures that they can test in the depths of the ocean or up in space. And I wonder if you could leave us with some advice. What are some things that, middle school and high school students should think about if they're interested in pursuing this path?
Awesome. Yeah, that's a it's individual for everyone, of course, but if you're interested in pursuing this path, we have so much knowledge at our fingertips, right? So much knowledge. So you have the power to look so many things up, and finding things that really speak to you. And there's so many videos online that explain things very, very well. So don't feel intimidated because this is something that you haven't heard of. It's always digestible, and there's always a way to learn it and really see if you like it. And it sparks that passion in you. If you just look it up and you start reading and looking through the material and getting into that, but also looking and not being afraid to talk to people and reach out to people that you see that work on these things. Give them a call, give them a text, an email, whatever way you can reach them. Or if you see them giving a talk or a presentation, always feel free to go up and have the initiative to strike up a conversation and say, be honest, I'm very, very interested in these things. I want to learn more. How do you propose that? How can I learn from you? These kinds of things, right? So definitely never be afraid, I would say, to talk to people and to reach out, specifically reach out. That's a very important thing to do. People are always just people, and so remember that. And they're always, most of the time, very, very happy to share what they do. It makes them happy.
Absolutely. That is great advice, Mariana. And now, before we go today, I just want to remind our Nord Anglia students that I'm really excited to see them next time for our abstract brain hacks for trick shots. And with that, I'd like to thank you all for joining us today. Thank you to all the students for asking such phenomenal questions. Thank you to the MIT Nord Anglia Education Collaboration for making this series possible. And thank you again very much, Mariana, for sharing your research and story with us today. See you all next time. Goodbye.